So C became popular because of its flexibility. It has structure and typing, just like a high-level language. It has low-level capabilities, and that means you don't need to use assembly language in the same way. So C has some big strengths, and its biggest strength is probably its support for pointers. That gives you flexibility. You can access memory and other devices very easily in your C code. Its biggest weakness is its support for pointers, which might seem a bit strange. How can it be the strength and a weakness? Well, it's a weakness because it's the biggest source of coding errors. So it's powerful, but you have to use it properly. So pointers, as I say, are both a strength and a weakness. You need to use them with care. Understand pointer arithmetic, and in particular, if you have a pointer that's no longer required, set its value to null so that it's easy to identify. And with pointers, you can sometimes get carried away, so avoid the temptation to have deep indirection. So a pointer that holds the address of another pointer is just about manageable, but if that in turn holds the address of yet another pointer and so on, it gets very quickly out of hand. So keep things simple. Let's take a quick look at how we might want to use pointers in our code. So here we have a simple array of 3 ints, and we can declare a pointer called map that's going to point to the start of that array. Okay, so that's all fairly straightforward. If I want to point to the next integer in that array, that's also very easy. I could just increment the value of map, and that will in turn automatically point to the next item in that array. Plus plus works, so too does plus equals, or even just map equals map plus 1. Okay, so pointer arithmetic is very easy to work with. Okay, so they'll all point to the same location. What if we actually wanted to point to the next byte though? So pointing to the next int in the array makes lots of sense, but sometimes we might actually want to process the memory byte by byte. Well, we can do that if we tell the compiler that we want to treat the map pointer as if it was pointing to individual bytes, and in C that means using the char type. So by doing a cast on map before we increment it, rather than going to the next int in the array, it simply goes to the next byte. Now, if we want to access the contents of any element in the array, then C provides a nice syntax for doing that. We can just use square brackets. So my array square brackets 2 is going to give us the third element in that array. So the index in a C array always starts from 0. I can get the same location by adding 2 onto map, because map points to the start, so map point plus 2 is going to give me the integer 2 further on in the array. Another way of doing the same thing is I can use the name of the array and add 2 onto it and then dereference it. So we're treating the name of the array as if it was a pointer. Might seem a little bit odd, but the compiler is quite happy to let you do that. Or we can even use the square bracket notation with a pointer, so treating the map pointer as if it was the name of the array. So I'm not saying that you should be doing this. It's making your code more confusing and therefore it's not recommended, but the C compiler is quite happy to let you do things like that. So if you're using C, you need a certain amount of discipline in order to make sure that you do things which are appropriate. Now, pointers are very powerful, so if we want to use a pointer to access a memory location, the syntax is fairly straightforward. So here we have a memory location, 8 followed by some zeros and then 4. So that's a memory address. If I want to access an unsigned int, value 7, that is going to be at that location, so this statement is going to write 7 into the specified address, then we can do that using pointers. So what we're doing in the syntax here is we're telling the compiler that that number, 0x 8, 0, 0, 0, etc. 4 is actually a pointer to an unsigned int, and then when we add another star there dereferencing it, that says we want to look at the contents of that memory location. Okay, so once you get the hang of that, using pointers to access memory locations is quite simple. But don't get carried away. It's tempting sometimes to write clever code just because you can. For example, what does this do, this block of code? So see if you can guess. So we've got an array. We've got 3 elements in that array, just some rather random looking numbers. And then we've got a very odd statement here where we've got some brackets, some stars, void, code array. So what on earth is that doing? Well, if you can't guess already, let's take a look at our next slide. That might give you a clue. So what we have now is we've declared those 3 numbers as constants. Okay, so we've got a name, move r13, move r31, and ret. So that might be giving you a bit of a clue because those numbers are actually corresponding to machine instructions. So we have an array that contains 3 instructions, and what's actually happening with our mystery line of code is that is actually going to treat the code array as if it was a function containing those 3 statements. So that line of code is going to execute the 3 instructions that are part of the array. Now, it might seem very strange, and you might even be surprised to find that it compiles, but it can work. Not recommended code at all, because it's just too obscure. But it's just an illustration of the fact that the compiler will let you do things that you might think are clever, but it's probably not clever because you might have to try and go back and make changes to this code in 6 months' time, and you won't remember what it's supposed to be doing. Okay, so remember that when you're writing your C code, typically developers spend far more time actually debugging their code than they do writing it. So bear that in mind when you're writing your code. Writing clear, readable code is the sensible approach to take, because that means that it's easy for you and other people to understand it. So in terms of priority, your number 1 priority really should be writing code that is clear and readable, because that makes it maintainable. It also makes it much easier to debug and find mistakes. A secondary concern would be efficiency. Now, we want our code to be efficient, but in general, that's the job of the compiler. So the compiler for C code normally does an excellent job at creating an efficient implementation from the C code that you write. Okay, so focus on writing clear and readable code, and the compiler will normally do a good job of optimizing that for you. So the sorts of things you can do to make your code more maintainable, maybe using variables to break down complex things into easier to understand steps. Okay, so if we've got a block of code here where we have a memory location, we're dereferencing a pointer to get the contents of that memory location, we're then doing some bitwise AND operation, and then doing a comparison. Okay, so that might work, but a better approach might be to actually define a constant to represent that address. Okay, so if that address is always going to be the same and it's going to be reused several times in different statements, having a named constant is going to make your code easier to understand. Okay, so now we can see that we're going to be doing an operation on the contents of my device and then comparing it with a test. We could add another variable for the actual device error. So in this case, device error is the result of doing this bitwise AND operation on my device. and then that's going to be either a 1 or a 0, so we can check to see is it 0 or non-zero, for example. So in terms of the efficiency, then you might be faced with a situation where you can write your code in multiple different ways. How do you decide which is the most efficient way of writing your code? And as I said, generally we can let the compiler take care of that. So here's a simple example. What we have in this case is we've got a block of code with an array, and then there's a for loop that's going to set each element of that array to 0. Okay, so it's just going to initialize the contents of that array. And you may look at that and think, well, that doesn't look very efficient because we've got a loop, and loops mean that your code is going to have to be jumping about, and you might think there's a better way of doing it. So our second alternative uses some more obscure programming. So we've got a union. So unions are used where you want to have memory locations which are shared between different variables. So we've got the array as before, and its memory space is going to be shared with this other unsigned whole. Okay, and then there's a statement at the end that's going to use the whole view of my var and assign it to 0 in one statement. So you might think, well, okay, that uses one statement, so that's going to be more efficient implementation. But in practice, that won't be the way that the compiler sees it. So compilers are very good at avoiding unnecessary loops. So the compiler will probably look at the unsigned array, look to see that it's simply initializing each element to 0, and do that in the most efficient way possible. So you may be surprised to find that there's actually very little difference in the instructions generated by the compiler for either of those approaches, in which case use the one on the left because it's much easier to understand and maintain. Now we can even go one stage further and say that it's not worth writing assembly in many cases because C does a better job. And let's take a look at an example using switch statements. And in this case we've got 3 random values in our switch, and we haven't included a default clause here just to keep the slide simple. So generally we'd always recommend including defaults, but we just missed it off here to keep the story simple. So these 3 random values, that's going to get compiled into some kind of if then else type logic. Switch statements are easier to read, which is why we've used them here. But it won't make any difference whether we had written that in assembler or in C. We'd still get the same sort of if then else type logic generated. Here we have another switch. In this case we've got 3 incrementing ints. Well, we'd expect a compiler in this case to actually convert that into a simple address table. Okay, so where the addresses are just incrementing. And switch statement in this case we've got 3 numbers incrementing, but there's a gap. So what would we expect? Well, probably just a simple address table with some dummy entries. And what we have in this case is a more complex switch statement, so a larger set of values. Well, that's likely to be implemented as a lookup table. Okay, so with lots of different values, we can sort of write the code in C very easily. Now, if you were to look at how you might do that in assembler, a smart assembler coder would probably write that in a very similar style, because they'd know from experience that changes are typically required in applications, so they'd write it in a way that's easy to modify, which ends up looking pretty similar to how we've done it in C. And the C compiler, I'd say, will build it to something that is just as efficient as the assembler implementation in most cases. If it doesn't, then you need to look at maybe compiler switches or getting a better understanding as to how the optimization switches on your compiler really work. So just to summarize this section, C is an excellent language for embedded. It needs to be used with care though, because it's very easy to write code that's hard to understand and hard to maintain. So clarity is the most important aspect. Recognize that the optimizer is normally going to do a much better job than you could by manually manipulating the code to try to give you more efficient implementations. So don't try to fight the optimizer. That's what we're saying here. And by all means, sort of try out some simple experiments to look to see are there some differences in the way you write your code. So maybe some styles of programming will be translated more efficiently by the optimizer than others, and then stick to those styles. And for complex designs, maybe C++ gives you a better approach than C, but that's going to have to wait for another day to talk about.
Doulos is a training company providing expertise and specialist training worldwide in all of the areas you can see on screen, from SoC design and verification, FPGA and hardware design, to embedded software and Python and deep learning. You can watch the rest of David's webinar, Why C is the Language of Embedded, whenever you want, by heading over to our website www.doulos.com/od and registering for free. For more free tips and tutorials, visit the know-how area of our website, and don't forget to subscribe to our YouTube channel. Thanks for watching.